Hello, this is Mr. Sorrentino, your friendly neighborhood math instructor here, presenting another video dealing with Math 31 and Section 2.3, which deals with the composition of functions. In 2.2, we did spend some time going over operations of functions and dealing with domains of those. There was one other operation that, that's unique to functions that doesn't happen with just regular expressions of numbers, and that's composition. In composition, which you see this little O symbol, don't get it mixed up with a multiplication symbol, which is like just a dot. This is an O, or a little open circle. This indicates composition, and basically what composition does is it takes the it takes a value, plugs it into one function, gets an output value from that, and that becomes a part of the domain of the new function, which I then plug in and get a value for that. It's a little tricky, but it's not extraordinarily difficult. It just takes a little getting used to. So let's demonstrate how to do that numerically, and then how to deal with dealing with functions that deal with that. And so you have some information about the composition of functions up here. I'm going to talk about what all the aspects of this in a moment, but that's generalizing everything I'm about to go into here. So as we do this, we have three functions: f of x, g of x, and h of x, and we want to carry through in A and B these compositions. Now notice that inside the parentheses I do have numbers. This means I should end up with a numeric answer. And a lot of people think that composition, like it's like multiplication, it's commutative, that I can, reverse the order and I'm going to get the same answer. That's not necessarily true. As a matter of fact, in many cases, it won't be true. So when I do f of g of 2, which is how I say it, a lot of people will say fog 2, but it's, f of g of 2, which basically is the same thing as saying f of g of 2. For me to evaluate this means following my order of operations, which means I always work with the innermost parenthesis first. I'm going to do g of 2, which means I'm going to go to the function g of x, replace the x with a 2, and so I'm going to have 2 plus 1 here, which is 3. So this is going to be f of 3, which means now I go to the function f, replace the x there with a 3, and get 3 squared minus 4, which is 9 minus 4, which is 5. Whereas for g of f of 2, I'm doing this, g of f of 2, which means when I deal with the innermost parenthesis first, I'm going to do g of, well, going to the function f, replacing the x with 2, I'm going to have 2 squared minus 4, which is 4 minus 4, which is 0. So g of 0 is what I have to evaluate next, which means now I go to the function g of x, I replace the x with a 0, and I evaluate it, and I get 1. So notice that these two values are different, which indicates that composition is not commutative. Do not get it mixed up with multiplication. Multiplication is commutative. So if I did f times g of 2 and g times f of 2, be the same thing. For composition, on the other hand, no. With composition of functions, if I'm going to come up with function rules where I compose two functions together, I can actually get some cancellations that allow certain functions to occur where, I may have had domain restrictions. Like for instance, h of x. When I look at these original functions, this one has a domain of all real numbers. This has a domain of all real numbers. And this has a domain, well, because of the square root symbol, I can't go anything under 5, or I'm going to have a negative underneath the square root. So 5 or more has to be the domain. And, if I do any kind of combination with h of x through addition, subtraction, multiplication, division, I'd have to account for that restriction and possibly others in the case of division. With composition, that doesn't necessarily have to be the case. So for instance, when I look at examples, and I'm going to go through the calculator momentarily to show how to do that for the calculator. When I look at the domains for these two functions, okay, f of h of x means I have f of h of x, which means that for this to occur, for me to be able to do this composition, because this is going to be f of the square root of x minus 5, that means that the square root of x minus 5 has to exist. For that to exist, that means that I have to have this domain of negative infinity, or take that back. I have to have my domain of being 5 to infinity in place. Otherwise, I'm not going to be able to go any further with this. The square root of x minus 5 has to exist. So, this means I'm going to go to the function f and replace it with the square root of x minus 5, which means I'm going to have the square root of x minus 5 quantity squared minus 4. If I work this out, squaring a square root is going to get rid of both. I'm going to cause a cancellation. And I end up with x minus 9. So f of h of x equals this function here. Now, if I was just presented with that function, I would say, well, there's no domain restriction. That's polynomial. You could subtract 9 from any number. But that's not the case. I have to say that my domain for this is 5 to infinity, because if the square root of x minus 5 did not exist, then I would not have been able to do this problem. So I have to be aware of that and be careful about that. So that restriction is not going to go away here. That has to occur for me to be able to even to do the composition. So basically this had to occur up here before this was allowed to be done. When I look at the reversal of those two, h of f of x, a little different. This is equal to h of f of x, which means I'm doing h of x squared minus 4. Now, for this here, x squared minus 4 has no domain restrictions. So far, my domain is all real numbers. That's great, because there's no restriction on what x squared minus 4 can be. I could take any number in the world, square it, and subtract 4. I'm going to get another real number. I'm not going to get any kind of undefined values by doing that. It's defined for this, so now I'm going to go to the function h and replace the x with x squared minus 4. So I'm going to have x squared minus 4 replacing the x. So the square root and the minus 5 are still going to be there. And if I carry this out, I get the square root of x squared minus 9. I end up with a function that has a square root symbol in it, but what I have underneath of it is different than what I had in h of x. This x squared minus 9 has to be greater than or equal to 0, which means that x squared has to be greater than or equal to 9. We have not gone into the process of solving inequalities beyond linear ones. We're going to be getting to that, I believe, in chapter 3. So, some of this is going to be a little bit more complicated. I'm going to kind of show a preview of, what this means here. But essentially, if you think about it, if I think about numbers, x and y, let's start with -5. If y equals x squared, this would be 25. If this is -4, this would be 16. If this is -3, this would be 9. If this is -2, I'd have 4. -1, I'd have 1. 0, I'd have 0. 1, I'd have 1 again. 2, I'd have 4. So it seems as though, if I keep going with this pattern, for x squared to be greater than or equal to 9, either x has to be greater than or equal to 3, because 3 is squared is 9, that's equal, 4 squared is 9, or x would have to be less than or equal to -3. Because squaring -3, squaring -4, squaring -5 would produce a value that's more than 9 as well, and therefore x squared minus 9 would be, positive, and I could actually do it. So as a result, this is the function I have. My domain in interval notation has to be that I'm either going to be less than or equal to -3, or I have to be 3 or more. And so that's my domain for this function. And it's not because, I needed that for this function to work to begin with. F of x was able to work with any real number. It's just now what I end up with as a result, only numbers that are less than -3 or less than or equal to -3 or greater than or equal to 3 can work in this new function that we got. So I have to account for that. So that's the difference when you handle compositions. Going back up to the original 2, which just dealt with finding numbers. And you have the calculator summary on this. What I'm going to do is I'm just going to, and I show you this on, on the sheet as well. But just kind of show you in more real time. If I take the two functions f and g, I'm going to let y1 be f of x. So I'm going to have the x squared minus 4. And I'm going to let y2 be g of x. It's going to be the x plus 1. If I'm doing numerical evaluations and I want to do f of g of 2, I can sit here and say, okay, I'm going to do y1 parenthesis take that back. y2 of 2, that would be the same thing as your f of g of 2, because this is f of x, this is g of x. F of g of 2 would be this. And as you can see, it is 5. And if I did the other one, g of f of 2, I would get the confirmation that that is the 1 again. So your calculator can do those sort of manipulations. I mean, I could actually, if I try to do that here, I don't know if it's going to do the simplification. If I wanted to do like, if I wanted to put like h of x in here, so say I would have the square root of x minus 5. And if I was down here, like down here again, and I want to do f of h of x, I might be able to do f, which would be y1 of h, which would be y3 of x. It would just keep it that way. It's not going to like come up with a nice expression for me to do along the way. So I could probably come up with a graph. That if I graphed one versus the other, I could compare. But I'm not going to be able to come up with anything that's going to like simplify it for me. And so there's no really use in doing anything more abstract than that. The last thing that you're asked to do in 2.3 is to basically do two other things. Example 2, you're asked to kind of do this very similar process of evaluating with numbers, but using a table. So let's have a look at that. So for example 2, you're given this table here, which has x values from -5 through 5, no in-between values. So if you would get to a situation where you're trying to figure out f of -4.5 for some reason, you're not going to be able to figure it out because it's not defined. And you're given values between -5 to 5, and you're given the f of x value. So this basically means that if I look here, this means that f of -5 is 32, f of -4 is 16, f of -3 is 8, so forth and so on. And likewise, this would be that g of -5 is 10, g of -4 is 8, g of -3 is 6, so forth and so on. So when I look to do these problems here, f plus g of 5 means, again, f of 5 plus g of 5. And if I'm using the table, f of 5 is -8. So I'm just going to the x value of 5, and I'm going to where f of x is, and that's -8. And g of 5 is -10. So I get a -18. So pretty straightforward. F minus g of x, or g of 3, I'm going to have f of 3 minus g of 3. And that equals, so f of 3, going to the table here, for when x equals 3, f of x is -2, so f of 3 is -2, minus g of 3, so when x is 3, g is -6, so that's going to be -2 minus a -6, which is -2 plus 6, so that's going to be 4. Likewise with multiplication, f times g of 4 is going to give me f of 4, or -4, times g of -4. So for -4, if x is -4, g is 16, or f is 16, times, when x is -4, g is 8, and 16 times 8 is 128. So with the table, it's pretty straightforward. When you get to composition, it gets a little bit more tricky. And that's because composition itself is a little bit more tricky. So when I do f of g of 0, it means I'm going to do f of g of 0. And I'm going to work my way from the inside to the outside. So I'm going to first do g of 0, which means I'm going to go to where x is 0, g is 0, when x is 0. So this becomes f of 0. And now I'm going to go to x being 0 and see what happens when f of x is 1 there. So this ends up being 1. Whereas if I do instead g of f of 0, Well, again, I'm going to go, we're starting here. When x equals 0, f of x is 1. So this is going to become g of 1. So now I'm going to go to where x is 1 and see what g of x equals. That equals negative 2. And lastly, for the division, this is the same thing as doing f of negative 3 over g of negative 3. So when x is negative 3, f of x is 8, so 8 is going to be on top. When x is negative 3, g of x is 6, so I'm going to have a 6 on the bottom, so I can say that's 4/3. I can say that's 1.3 repeating for 1 1/3, whatever way you want to say it, but there's the answer to that. So the table is not very difficult as long as you're taking your time and paying attention to what's your x value at the given moment and then what's going to be your right y value. Because remember, these two guys here are y values. They're two different y values. They're defined differently, but they're y values. The last thing you're asked to do is essentially a decomposition. They're telling you that here, h of x is the composition of f of g of x, and that's equal to 2 plus x cubed, 2 minus x cubed to the 6th power. They want you to find functions f of x and g of x such that this is true. So, I'm basically saying that h of x is the result of me composing these functions together. There's different variations I can do this. I had to kind of be on the lookout, though. I had to say, okay, what's going to be my innermost function, which is g of x, and what's going to be my outermost function? So one instance, I could look at, this being my g of x, and then the raising to the 6th power being my f of x. So one possibility would be for f of x to equal x to the 6th power and g of x to be 2 plus x cubed over 2 minus x cubed. That's one possibility. Another possibility is to kind of focus and say, well, what if these were my g of x's? And notice they're both in both parts here. So my g of x was the x cubed, and that's what's getting placed into f of x. And so f of x could have been 2 plus x over 2 minus x raised to the 6th power as well. But both of these would, if I did f of g of x, would become the same function, h of x. So, and there's others too. I'm not going to go through every one of them, but you could probably come up with some other possibilities along the way and come up with other possible values for this. So, yeah. So, I mean, so try to come up with some more if you can, to try to see if you can come up with other things that would compose. And the ultimate test is simply, do your f of g of x and see if you get back to that 2 plus x cubed, 2 minus x cubed, all to the 6th. When you do that, if you work it out and it does, that's another combination that would work. I gave you 2 of them here. See if you can come up with some more. And that's the end of what I wanted to go through in 2-3. So if you have any additional questions, please make sure to bring them up in class or my office hours. But until I see you in one of those places or until the next video, have a good day and I'll see you around.